So the first thing I want to do is go over some calculations with how you calculate equilibrium constants. And you have to be given the concentrations in molarity, and then you also have to write out the equilibrium constant expression. So for this reaction, right, it's carbon monoxide plus 2 hydrogens makes methanol. So what I'm going to do is I'm going to do this. I'm going to call this A, I'm going to call this B, and I'm going to call that C. So then I'm going to write K is going to be equal to, and then it's going to be C at the top, because remember it's products over reactants, divided by A times B. And then because there's a 2 here, I'm going to put a square. Now, I didn't put brackets because you're supposed to have brackets for molarity, but I'm treating A as the molarity of A and B as the molarity of B, so it makes the notation a lot simpler. When you do this, for example, or you on an exam when you're told to write the equilibrium constant expression or to which of the following is the equilibrium constant expression, make sure you look for the one with brackets because that's how it'll be done. But as far as doing the calculations, it's very simple just to write A, B, and C. So the next thing you'll do is you'll go ahead and you'll plug in the values. So we're going to have 0.0274. And we leave off the units. That's one of the nice things in equilibrium constant calculations. The only time it's acceptable kind of to do that. And then I'm going to have 0.105. And then I'm going to have 0.114. And that's squared like that. And then all that's left is to do it on the calculator. Now this calculation will sometimes give people problems. So I actually did it once already. I'll go ahead and do it again. So I'd like to show it on the calculator just so people don't get too confused. 0.0274 divided by 0.105, and then divided by, and then 0.114, so 0.114, and then I'm going to use the square button, and then I'll hit equals. And that comes out to be 20.08, like that. No units in the equilibrium constant. Now I have 3 significant figures in all these numbers, so this answer should be 20.1 as the equilibrium constant. Okay. Now let's say we have concentrations for carbon monoxide and concentrations, as a bracket over here, concentrations for methanol. But we want to calculate the concentration of hydrogen gas in an equilibrium mixture, right? This calculation turns out to be somewhat more difficult because you have to rearrange the equation. So I'm looking for, in this equation, I'm still using this. This is still the same equation. It doesn't change just because you change the numbers. It's always going to be the same. But now I'm looking for the concentration of hydrogen gas when the equilibrium constant is 20.1 like this. So what you have to do is you have to rearrange the equation and solve it for B. So just very quickly, it's going to look like this. B is equal to, actually B squared, let me go to there. It's going to be equal to C over A times K, like that. And then I have to take the square root of both sides. And that'll give me this. Okay, so you notice if you're not good at the rearranging, you really do need to practice these things. But basically, I just multiplied both sides by b squared, and that's how I got to be on the top and canceled from here. And I divided both sides by k, and so that's what gives me this equation. And then I took the square root of the whole thing. It's usually the last thing you want to do. And that gives me the equation I have to solve for. So now, if I want to know the concentration of the hydrogen gas under these conditions, then I'm going to say B is equal to the square root, I'll leave myself a lot of room here, C, which is the methanol in this case, is 0.058. Right? Concentration of CO, which is A up here, sorry, I'm pointing with my finger, A up here. Right, that's going to be 0.250. And K, we'll use the value from before, 20.1. That number is the same as long as the temperature doesn't change. So anytime you have this reaction, that's going to be the equilibrium constant. So now again, I'm going to pop this into my handy dandy calculator. I'll move it to this side, otherwise it'll be in the way. So I'm going to go 0.058 divided by 0.25, and you don't have to type the 0, right? Divided by 20. So that gives me the inside part here. I just went ahead and just calculated it like that. And then I have to take the square root. And your calculator may or may not have a square root function, but you can go y to the 0.5. That's the half power, that's the square root. It ends up being 0.108 or 1077, right? And this only has two significant figures in it, so it's going to be 0.11. And because it was an equilibrium constant and all the other units were molarity, the concentration units pop back up here. So that's the concentration for B under those conditions. Now the last thing, and I don't think I'll make a separate clip for this, is to talk a little bit about activation energy and how it affects or doesn't affect, right, a catalyst and equilibrium, or how it isn't affected or is affected. So the activation energy is the amount of energy you need, right, for a reaction to proceed. And what a catalyst does, it lowers the activation energy. And so you can make a reaction go faster by increasing the temperature, which doesn't affect the activation energy, or you can find a catalyst which does affect the activation energy. And because the activation energy is lower, there's less of a threshold needed to break the bonds, and so the reaction's going to go faster. A lot of times the way a catalyst will work is there's a certain collision that needs to take place for a bond to break, and it forces the right orientation for the collision. And it often does that by holding the two molecules that are reacting together in such a way that they collide the right way. So catalysts lower the activation energy. But it turns out, right, that equilibrium is not affected by the activation energy or by the catalyst. So think about a reaction that's exothermic. Let's say you're in a car, right? And you're driving on a road and it's got a hill like it, like this. Oh, I made a lump out of my car. Here's my little car like this, and he's going down. It's going down this hill, right? This is the activation energy. How big the hill is that you have to go over before you go down. This is your activation energy, often abbreviated as EA. And so basically, what a catalyst is it just takes that hill and shaves it off and makes it smaller. Okay, and it does that by holding the reactants in a favorable way so that they can react. That's kind of often the way it is. No, not always, but often the way it is. The equilibrium is really determined by the height here. So that height between where the car starts and where it ends is independent of how big the hill is that goes in between. So it turns out equilibrium is only affected by that height, and so the catalyst and the activation energy have no effect on that.